Hello, IBSL2. So I'll just be working through problems 2 through 8 on this video. And number 2, the question says, if two 3D vectors are equal, this means that the magnitude and the direction are the same. So just like with two-dimensional vectors, 3D are the same. For them to be equal, the magnitude and the direction have to be the same. Okay, for question 3, it's telling us there's a quadrilateral that has vertices A, B, C, and D. And it wants us to find vector AB and DC. And then from what we find in A, it wants us to tell us what can we deduce about this quadrilateral. So let's just start by finding AB first. Okay, so AB, remember we're subtracting the B. We have B values minus the A. So 3 minus 1, and then negative 3 minus 2, and then 2 minus 3. So vector AB would have coordinates of 2, minus 5, and negative 1 for x, y, and z. Okay, let's find our vector DC now. So we'll take our C values and subtract the D. So we have 7 minus 5, negative 4 minus 1, and 5 minus 6. And our DC vector would have an x component of 2, a y of negative 5, and a z of negative 1. So we can see that vectors A, B, and DC are going to have an equal magnitude, and our directions are going to be the same since they're equal in components. So we can deduce that our quadrilateral has two sides that are parallel, and that would be AB and DC. Okay, all right. Okay, let's look at problem number 4. And we have find R and S given our A vector and our B vector, and A is parallel to B. So remember, for if vectors are parallel, then one vector, and let's say it's A, would be equal to K, some type of scalar, times the other vector. So they're parallel. So let's set this up. Each component should have the same relationship. So our A times KB should work for each one. So let's go ahead and set that up. So 2 needs to equal KS. Negative 1 needs to equal K2. And then R needs to equal K negative 3. And these are all times here. So the only one of these three they're going to let us solve for K is our middle one here. So let's go ahead and solve for our scalar of K. So 2K is equal to negative 1. So our scalar must be negative 1/2. And then we just plug in to find S and R. So let's plug into this formula. So 2 equals our K we found is negative 1/2. And then we solve for S. So we multiply both sides by negative 2 here, our reciprocal. So that'll get S by itself. And S will be equal to negative 4. Okay, for R, it's a little bit even faster. So r is equal to k, which is negative 1/2 times negative 3. So r is equal to positive 3/2. Okay, for problem number 5, you'll need to know that what I, j, and k are. And the following vector in unit vector form I, j, and k is asking you to know that I is the vector in the positive direction for the x-axis, so unit vector, so 1, 0, 0. And then j is the unit vector in the positive direction for the y, so 0, 1, 0. And then k is the unit vector for z in the positive direction, so 0, 0, 1. And this is one of the forms you'll need to know. We've mostly been talking about component form, but you also need to know unit vector form. So I want to show you how that works. This is what we've been talking about up until now, but you probably remember from last year the unit vector form. And what you do is you take each component and multiply by I for the x, so a would be equal to a1i, and then plus a2j plus a3k. So the x component gets multiplied by I, the y component gets multiplied by j, and the z by k. And this is called unit vector form. So you need to know when you see that, that's what they're looking for. And when you see the words component, that's you're looking for the component form, what we've been using mostly up until now. Okay, so for number 5, we're just going to write it in the from the component to the vector form. So we just take each value, and a would be equal, so for 2, our a1 times our I, so 2i, and then our a2 times j, so 0j, and then our a3 times k, so we negative 5k. And we don't have to have 0j, so we'll simplify that to a is equal to 2i minus 5k. And that's in unit vector form. Okay, for number 6, they're asking for the dot product. So I think on your paper, if you printed the notes, has that dot in the middle. So that's signaling dot product. And the same principles apply as we did it in 2D. So go ahead and try the dot product in 3D. The same thing, we'll be multiplying the x plus the multiplication of the y plus the multiplication of z. And then start the video again. Okay, for number 6, I have here in purple, and the dot product would be found, and you would get negative 4 for the dot product of P and Q. All right, for number 7, we have another definition. So make sure you add that to your notes. If x divides AB, then AX is parallel to XB, or you also know that AX is equal to a K times the vector XB. And for our points A, B, and C, what it means by collinear is that collinear is 3 or more points that are on the same line. So if I drew a line in 3-dimensional, let's just say this is the line 3-dimensional, A, B, and C would be on the same line. That's what it means by collinear. Okay. And they want us to prove that points A, B, and C are collinear, and we do that by showing that they are parallel vectors. So our vectors are parallel. And it's important to keep reading this problem because it wants us to know the ratio in which A divides CB. So that's important to think about. They're wanting to know how A divides CB. And so we're going to set up with our vector A in the middle, our point A in the middle, as it reads this problem. So let's change that. So it's A is going to divide CB. So let's put A in the middle. And then we'll set up our vectors then for A in the middle. So, and they want CB. So we're going to have CA we need to show is parallel to AB. So let's find those two vectors. Okay, so go ahead and pause the video and find those vectors and bring it back. Okay, so if you found vector CA to be -21, -7, and 14, and AB to be 6, 2, and -4, you're on the right track. Now we're trying to prove that these vectors are parallel. So if you look at the vector components and think of how we could simplify them, the first thing that comes to mind for me for CA is that there's a factor of 7 in each value. So and then I'm also seeing that there's more negatives here than positives. So I'm going to go ahead and see if I were to divide out a factor of 7 and also a factor of -7, so if I multiply by -1/7, that would make CA equal to 3, 1, and -2. And then I can see there's a factor of 2 in each component of AB. So if I divide each component by 2 or multiply by 1/2, I can see that my two vectors will be equal. So therefore, I can show that these two are parallel. And in particular, I want to show that CA has, if you multiply a scalar times AB will equal CA. So if I'm looking at these two factors, I'm going to go ahead and multiply -7 over 2 times my AB for it to equal CA. So go ahead and pause the video and try that and make sure that works. Okay, so you should have gotten that my scalar of -7/2 multiplied by AB does equal CA. Now we want to write that succinctly, so we're going to be saying that A does divide the ratio that A divides CB would be -7 to 2, and specifically I would write that as A. Therefore, A divides CB internally in the ratio of -7 to 2. Okay, let's try the last problem, number 8. And 8 is very similar to 7.3. We're talking about angles and finding our angle. And we're going to be using our cosine rule. And we'll set this up in 3D the same we would as 2D. So we want to know our angle of ABC of our triangle. So we're finding angle B. So with our points here, we're going to be setting up appropriately and solving. If we solve for B, we want to find the vectors BA and BC. So go ahead and try that. Find the vectors BA and BC, and then plug in and into your dot product with the cosine and find your angle using that formula and bring it back. Okay, so if you found BA and BC to equal these vectors, you're on the right track. And then you should plug into your formula. You find your dot product of BA and BC and divide by the magnitude of BA and BC. and that would result in 9 over the square root of 380, and then if you take the inverse cosine, you get 62.5 degrees. Okay, thanks so much.